I welcome you all for the week 9 live interactive session for the course Polymers, Concepts, Properties, Uses and Sustainability. So, as usual, we'll get into the recap of the lectures of week 9. So, week 9 had 8 lectures. The first few lectures were based on the concept of interaction of polymers with other materials. So, lecture 62 covered compatibilizers, that was on uses. So compatibilizers for blends, different roles of compatibilizers, type of compatibilizers, and then reactive compatibilization, and fiber treatment and sizing, like surface treatment, coupling agents, sizing of the fiber, components for sizing of glass fibers. Hello Nirmal.
Yes, ma'am.
Good evening. So we'll
Good
just
evening.
go through the recap of the lectures. Okay.
Okay.
Yeah. So lecture 62 was based on compatibilizers, right? So compatibilizers for blends was discussed, and then role of compatibilizers, like it reduces the uh, it helps in increasing the dispersion, uh, right? And then the types of compatibilizers was discussed, and then what is reactive compatibilization was discussed, right? And then fiber treatment and sizing, how sizing is important, and the surface treatment, coupling agents, and sizing of fibers and all were discussed, right? And components for sizing of glass fibers, and then role of sizing in glass fibers were all discussed, right? And then the next was on natural fibers and polymers. So how, you know, cellulose, which is hydrophilic fiber, and hydrophobic or partially polar polymers are mixed to form a composites, was discussed. And then compatibilizers or sizing key for mixing the uh, waste for plastic recycling, how different types and components of compatibilizers and these kind of fillers and all, it plays a very vital role in helping plastic recycling was all discussed, right? Are you there, Nirmal? uh, you can unmute and
Yes,
speak.
ma'am.
Yeah, you can unmute and speak. Okay, I won't be able to see whether you're there or not, so just give me a response whether you're able to recollect the points and you're able to understand. Okay.
Okay, okay.
Yeah, sure. And then lecture 63 was on biopolymer applications, right? So here, Xanthan Gum, which is very widely used as a thickener, was discussed. And then different interactions that's happening in Xanthan Gum was discussed, right? And then the application of xanthan gum in various applications like food applications was discussed, and how what is the conformation in its in solid state, and how is the conformation in a solution state, and how the xanthan gum acts as a viscosity modifier, with the explanation on the structure was all discussed, right? And this was followed by natural rubber, where uh, the polyisoprene, the natural rubber, was discussed. And then the elastomera vibration mount, how it is really used, and how it, the non-interactive behavior, uh, uh, you know, just the segmental mobility, it plays a very vital role, in vibration mount, right? How it, protects from vibration, or how it helps in damping and all was discussed, right? And its closeness with the ideal system, like for example, in case of an ideal gas, it is it doesn't interact, there is no molecular interaction, right? The molecules are widely placed. So similarly in polyisoprene also, in natural rubber also, There is no interaction between the macromolecules, but it is more of the segmental mobility that plays a very vital role. And the compare and contrast between the xanthan gum, where interaction plays a very vital role in its application, whereas in case of polyisoprene, where there is no uh, bigger interaction between the macromolecules, but it is more of the segmental mobility that and the ideal behavior that really plays a vital role in its application was discussed, right?
Yes, ma'am.
Yeah. Did you go through the lectures?
Yes, ma'am. I've
Okay.
gone through the lectures.
Okay. That's nice. That's nice. Just try to recollect when I say the points, okay? And if you're getting any doubts, you can just ask, okay?
Okay, ma'am.
Yeah. And then uh, again, lecture 64 was also based on interaction of polymers with other materials, where adhesives and paints was discussed, right? So different application of adhesives, and then the structural adhesives and mechanism of adhesion was discussed. Okay, the type of failure of adhesive material was discussed, and then different adhesive formulations were also discussed, right? And then next, paints were discussed. What are the components of paints, and how how the polymers play a role, uh, right?
Yes, ma'am.
And then the water based paints, the associative thickeners, where it has a hydrophobic ends. Do you remember the picture where the hydrophobic ends had this R1 and R2, the hydrophobic components, whereas the inner portion it did have the hydrophilic components, right? It was amphiphilic
Yes,
in
ma'am.
nature, right?
Yes, ma'am. Yes, ma'am.
Yes. And then the focus moved on from the interaction of polymers with other materials to polymer processing and recycling techniques in this week. Okay, so the lecture 65 was on dissolution and recovery, right?
Yes, ma'am.
And this was basically focusing on the sustainability, uh, sustainability aspect, right? Where the mechanical recycling, the processes and challenges involved, even during the shelf, service life as well. There might be some end groups which might be subjected to some kind of oxidation. Okay, that is why the mechanical recycling really doesn't help, right? And then chemical recycling was discussed, and the process for chemical recycling, and how the CO2 equivalent emission index was explained for different type of recycling, especially where this dissolution process showed a better value, right, compared to other solvation and other techniques, right? And
Yes,
then
ma'am.
how the macromolecules are recycled through dissolution. So examples were discussed, and then recovery of solvent, which becomes very critical. When you use some organic solvents, again, the sustainability becomes a question mark, right? Like which has some health, it might have some health issue related things, or some other sustainable issues, right? And how the dissolution rate, it plays a very vital role, because this becomes a complex system, right? It has different layers with liquid layer and the polymer layer, and then a swollen gel layer, right? And then a rubbery layer, and finally a glassy layer in case of thermoset polymers, right? So how the solvent polymer interaction, it plays a very and the dissolution of the solvent, the diffusion of the solvent through the polymer so as to dissolve of the polymer, how much critical it is, and then how the criticality further builds up when there is an in case of a what to say, so a semi-crystalline polymer, it's not amorphous, it's a semi-crystalline polymer. The complexity further builds on in case of a semi-crystalline polymer, right? And then the anomalous diffusion process. So it doesn't follow a Fickian behavior. It goes from a Fickian to a non-Fickian behavior because of the complexity and the different layers in the system involved, right? Okay, so those things, all those aspects were discussed in the lecture 65. And then further focusing on the polymer processing and recycling techniques were continued, and lecture 66 was on polymerization kinetics, right? Do you remember what are the polymerization kinetics that was discussed?
Yes, ma'am.
Do you remember anything? Can you name some?
Free radical step growth polymerization.
Yes, yes, free radical step growth polymerization. So polymerization operations were discussed, and then polymer manufacture, different aspects of that: polymer manufacturing, polymer processing, reactive processing, and then composite processing was all discussed, right? And then kinetics of free radical polymerization, and then step growth polymerization. Can you just name any one polymer that undergoes free radical polymerization? Do you remember anything?
No, ma'am, I forgot it.
You have forgotten. Okay, that's okay. Your polyethylene, right? This double bond, they form the free radical, and that polymerization continues. Similarly, polypropylene and all, it undergoes free radical polymerization, whereas step growth polymerization is, it's your polyesters, right? It's nothing but a condensation polymerization, right? And then
Yes, ma'am.
kinetics of living polymerization. Both living polymerization is nothing but your uh, ionic polymerization, both cationic and anionic polymerization, right? And cationic polymerization, it so different cationic polymerization follows different kinds of kinetics, so there is no generalization. Whereas only in case of anionic polymerization, there was a generalized formula that was discussed, right? Do you remember that? I mean, not the formula, at least uh, you know that this concept was discussed, that cationic polymerization, uh, you know uh, it's difficult to bring it into a single formula, right? Are you there? Maybe if you're finding difficulty, you can just type in the chat box as well, okay? And then the lecture 67 was on polymerization reactors. This was again on uses. So what are the different modes of polymerization? Like industrial polymerization processes were discussed, where bulk polymerization, solution polymerization, precipitation polymerization, right? Suspension, and then emulsion polymerization. So compared to a suspension polymerization, emulsion polymerization is better one, where you can control the uh, you know uh, molecular size and all, because of the presence of surfactants was discussed. And then gas phase polymerization was discussed. And then how these different type of polymerization are industrially applied. What are the different type of polymerization industrially applied for manufacture of LDPE, which is a free radical polymerization. And then for HTP and polypropylene, using Ziegler-Natta and metallucin processes, what are the different type of polymerization techniques that are used? And then for polystyrene, free radical, which is also based on free radical and metallolysis process. And what are the industrial polymerization process for that as well was discussed. And then some more examples were also discussed, right? And then lecture 68 was on polymer processing. It was on concepts. So where processing of polymeric materials was introduced. So what are the different unit operations that are involved during polymer processing was all explained. And then the tool requirement, like your die, right? And then what are the processing techniques, right? Injection molding, extrusion were all discussed. And then what is the flow behavior, and then how does the flow behavior vary in case of a liquid crystalline polyester. And then processing and properties, how processing determines the properties, and how both are determined by the molar mass was discussed. And then melt flow index measurement was discussed. And then there was a discussion on dimensionless numbers, right? Deborah number was discussed, Weisenberg number, Reynolds number, elasticity number were all discussed in this lecture. And then the final lecture for the week was again on polymer processing, which was on uses. So here extrusion process was discussed, right? Single and twin screw extruder, where the single screw extruder was explained in detail, and the extruder characteristics like extruder variables, die opening, pressure drop was discussed, and then injection molding process was discussed, where its operation, and then processing window, and then analysis of the processing operation was all discussed, and then what is the idealized flow, right? Poiseuille and cuvette flow, and then the complex geometries involved, phase change involved, heat and mass transfer processes involved, and then the reactions involved were all discussed, right? Are you there, Nirmal?
Yes, ma'am.
Okay. Okay, so that's nice. Now let's go on to practice assignment of this week 9. Okay, following graph shows operating window for a extruder. So two speeds of the extruder screw rotation, RPM 1 and RPM 2 are shown in the diagram. So RPM 1 and RPM 2. Okay, and also flow characteristics for two dies, right? Die 1 and die 2, the diameters of die 1 is d1, and the diameter for die 2 is d2, okay, respectively are shown. Now just answer me this question. Do you remember this diagram in the course lecture, Nirmal?
Yes, ma'am.
Yeah, okay. So this was the flow rate versus the pressure drop diagram, right? So just answer me this question. Which of the following is correct? Die 1 having higher diameter than die 2, and RPM 1 is greater than RPM 2, or is it die
Yes, ma'am.
1 having greater diameter than die 2 but RPM 1 is less than RPM 2, or is it die 1 having lesser diameter than die 2 and then RPM of 1 is less than RPM of 2, or is it die 1 having lesser diameter than die 2 but RPM 1 is greater than RPM 2? Which of these is right? Take a minute for thinking over it. Just look into the plot.
Diameter 1 less than diameter 2.
Okay.
Diameter 1 less than diameter 2.
Okay.
RPM 1 less than RPM.
Okay. So how do you say this? How do you say this?
Based on the flow rate value.
Based on the flow rate value.
Or the pressure and flow rate value.
Based on the pressure and flow rate value. Yes, you are right. So the die 1 will have lesser diameter than die 2, as you said. Say for the same pressure drop, the flow rate for die 2 is high. So in order to have a higher flow rate, obviously it should have a larger diameter for the same pressure drop. And similarly, the RPM, right? Okay.
Yes, ma'am.
Yeah. Now let's go on to second question. So when I'm reading out the question, just mute yourself, and then when you're answering, just unmute, because I think there is a lot of disturbances from your end, right?
Okay, okay.
Yeah. Okay. So second question is, during a polymer processing operation, Q1 is a flow rate and delta P1 is a pressure drop requirement. Okay. So in order to increase the production rate, or for the faster production rate was required. Okay, due to which the flow rate is increased by 10%, which is given by Q2 is equal to 1.1 time of Q1, because there is an increase in 10%, right? So obviously the Q2 will be 1.1 times of Q1. Based on Hagen-Poiseuille equation, for the Newtonian fluid, the pressure drop will be delta P2 will be equal to 1.1 times of delta P1. Now tell me, for a shear thinning polymer melt, which of the following relation will be valid? So will it also have delta P2 equal to 1.1 times of delta P1, or will it have delta P2 1 by 1.1 times of delta P1, or will it have delta P2 greater than 1.1 times of delta P1, or will it have delta P2 less than 1.1 times of delta P1? Which one of the following is correct? Now you can unmute Nirmal.
Yes, ma'am.
So are you able to understand the question?
Yeah, ma'am. Just reading the question.
Okay. So what are the things that are given in the question?
Ma'am, it will be less than delta P2 is less than 1.1 delta P1.
How do you say that? Which clue made you think that delta P2 is less than 1.1 of delta P1?
So here the pressure is dropping.
Pressure is dropping, right? That's fine. But are you able to follow the question? See, initially there was some flow rate and there was some pressure drop, okay,
Okay.
for a particular process. And after some time, the operators, they wanted higher production, so they changed the flow rate to they increased the flow rate by 10%, okay.
Okay.
And they are saying that if it is a Newtonian fluid, since they have changed the flow rate by 10%, they say that the pressure drop would have also increased by 10%. And now they are asking, in case if this Newtonian fluid is replaced by a shear thinning polymer, then
Okay.
for the second set of flow rate, that is in 10% increased flow rate, what will be the pressure drop? That is what is their ultimate question. So will it be same as will it show a similar behavior as that of the Newtonian fluid, where the new pressure drop will be 1.1 times of the old pressure drop, or will it be less than that of that, or will it be greater than that of that, or will it be of that some ratio of that? That is what they are asking.
So here the shear thinning polymer is not like a Newtonian fluid one. So
Yes,
there,
yes. Now we have got the logic right. Okay.
yes, yes, yes,
Yes,
ma'am.
it is this shear thinning polymer. Since it is shear thinning, what happens? The viscosity will decrease in this case.
Okay.
Correct? Shear thinning
Yes,
means
ma'am.
it starts thinning out. So what happens? There is a viscosity drop.
Yes, yes.
So since there is a viscosity drop, the flow will be more. So you need not have lot of pressure difference
Pressure
in
too.
order to move the
Yes, ma'am.
fluid. Right?
Yes, yes, ma'am.
So that is why whatever you said is right.
The
That delta P2 will be less than
still
1.1 times of delta P1.
you
Okay.
want.
So this we can also say by, you can just mute yourself. I'll also explain the other way of explaining this better. So they have given that the Newtonian fluid and it's based on Hagen-Poiseuille equation. So if you see the Hagen-Poiseuille equation, it is given by delta P by L is equal to 128 mu Q by pi dt par 4. So where delta P is your pressure drop, L is your length, and mu is your viscosity, Q is your flow rate, and D is your diameter. Now, so according to the above relation, you can see that delta P, your pressure drop, is directly related to your flow rate as well as your viscosity. So since the polymer is shear thinning, keeping all other parameters constant, so here two things will change. One is the flow rate. Flow rate is changed in the process from an initial flow rate to a 10% increase. The second thing is that because of the material behavior, the viscosity is going to change. The material is going to thin out or due to the flow. So because of these two parameters, you can say that the flow will be more and your delta P2 will be the pressure drop required for the fluid to flow. The new pressure drop will be less than 1.1 times of the old pressure drop. Okay, that's it. So you're able to get it right?
Yes, ma'am.
Yeah. Let's go on to question number 3. If a combination of naphthalene and sodium is used to initiate polymerization of styrene, then the most likely mechanism of polymerization is it a free radical polymerization, or is it a cationic polymerization, or is it an anionic polymerization, or is it olefin metathesis? Which one it would be? This is the GATE question. This was asked in GATE 2019. So styrene is to be polymerized and they are adding naphthalene and sodium. And they have asked what is the probable mechanism of polymerization. Hello Uday Kumar.
Sir,
So uh, we started getting into the practice assignment and we are discussing the third question. Okay.
okay.
So just go through the question. So I'll also say the question once again. So if a combination of naphthalene and sodium is used to initiate polymerization of styrene, then the most likely mechanism of polymerization is it a free radical polymerization or cationic polymerization or anionic polymerization or olefin metathesis?
Anionic polymers.
You're saying anionic polymerization. How do you say anionic polymerization? And what
Uh,
made you say anionic polymerization?
some naphthalene and sodium can uh, electron withdrawing.
Hmm. What happened? Samir, you are getting? Nirmal, do you also agree it is anionic polymerization?
Yes, ma'am. For the styrene, it would be anionic polymerization.
Okay, but how do you identify from this question? Is there any clue that helps in this question to say that it might be possibly anionic polymerization? Maybe you can just mute yourself and you can type in this chat box. You both want to think for a while, or shall I say why and how?
because sodium contain electron withdrawing group, so it can participate in anionic polymerization.
Is it electron withdrawing group sodium contains? What is an anion? Anion takes up electrons and becomes electronegative, right? And becomes an anion, right? Cation,
Yes, ma'am.
it gives off electron, right? So
Yes, ma'am.
one clue, as you said, is sodium. So sodium, it'll ionize, you will get sodium ion Na plus. Okay, and in the process, it can initiate in formation of an anionic group in the system. Okay, and this styrene anion, it will start polymerizing. Okay, and that is why it is anionic polymerization. Okay,
Okay.
yeah. So, as Nirmal said, yes, styrene, it undergoes anionic polymerization through different kind of initiators. So this is one of the initiator that supports in polymerization of styrene. Okay, okay.
Ma'am, but styrene can participate in all anionic, free radical, and the cationic.
Yeah, different type of polymerization, yes, it does have. And anionic polymerization is one of the common technique for polymerization of styrene to form polystyrene. Okay,
Okay.
yeah, okay. uh, the plot shows the next question is, the plot shows apparent viscosity versus shear rate, okay, of a Newtonian, dilatant, and pseudoplastic fluids. So based on this plot and the fluid behavior as mentioned below, find out the correct combination. Now, uh, you have been given three numbers. Number one is dilatant fluid, number two is Newtonian fluid, and number three is pseudoplastic fluid. Okay. Now we have to identify which of the plots matches with dilatant, and which one with Newtonian, and which one with pseudoplastic fluid. Okay. So this is a GATE 2018 question.
Ma'am, option C, ma'am.
Option C. So you're saying P represents Newtonian fluid, and
Yes, ma'am.
Q represents uh, sorry,
Pseudoplastics.
Q represents pseudoplastic, and R represents dilatant. Okay, how do you say so?
In Newtonian fluids, the viscosity will be constant, ma'am.
Okay,
So it will be a straight line.
okay,
And in pseudoplastic, the upon on giving shear rate, the viscosity reduces.
okay. It is nothing but your shear thinning, right?
Yes, ma'am.
Okay, and dilatant is your shear thickening, right?
Yes, ma'am.
Yes, you are right. So Nirmal, you are able to follow that?
Yes, ma'am.
Okay. So there was a discussion again on based on the shear rate versus shear stress, right? During the class, right? How does the shear rate versus shear stress varies for a Bingham plastic, pseudoplastic, and dilatant fluid and Newtonian fluid, right? So you are right. Now let's move on to question number 5. Identify true or false. Compatibilizers decreases the interface thickness.
False, ma'am.
Okay. What will it do?
It actually increases the interface thickness and strength,
Okay.
and avoid the collisions of the different particles.
Yes, you're right. So the answer is false. So the action of compatibilizer is to increase the interface thickness. Okay. So that you will have a bigger interface region where one is in two and two is in one. So there is much more blending. Okay. Okay, that's right. Now let's move on to question number 6. In xanthan gum, the extended chain with helical conformation in solid state is due to which causes this extended chain with helical conformation in case of a xanthan gum. Are you both there?
Yes, ma'am.
So, do you remember the lecture where xanthan gum and your polyisoprene, your natural rubber was discussed, and the compare and contrasting where in case of a xanthan gum, the interaction plays a very vital role in its application, whereas in case of uh, you know a polyisoprene, it behaves more of kind of ideal where it's more of the segmental mobility rather than interactions, right? So I'm just giving a clue on that. Now tell me which interaction. So do you remember what is xanthan gum made of? Are you both there?
Yes, ma'am.
So what is xanthan gum made of? It is from a bacteria, right?
Yes, ma'am.
Yeah. So what is it made of? So it is a natural polymer, right?
Yes, ma'am.
Yes, natural polymer. So natural polymers, one of the three major classification, do you remember? Polysaccharides, proteins, nucleic acids, right? Which one
Yes,
does
ma'am.
which one does it come under? Are you able to recollect anything, or shall I say the answer?
Say the answer, ma'am.
Okay, so it is actually your hydrogen bonding. Do you remember this? The diagram of xanthan gum. Xanthan gum is a polysaccharide. So polysaccharides, it will be made up of either glucose, fructose, or some kind of these kind of sugar kind of units, right? So obviously, so xanthan gum is made of more of it has glucose unit which forms the backbone, and it also has some galactonic acid units and all. So obviously, these glucose and all, it will have this hydroxyl group, and this galactonic acid means you will be having COH group, right? Carboxylic acid group. So obviously these groups will have hydrogen bonding, and because of this hydrogen bonding, there is a helical conformation. Okay, extended helical chain conformation in solid state. This was actually taken from your lecture only. Okay, you are able to get it.
Yes, ma'am.
Yeah. So OH and COH groups. So it causes both intramolecular and intermolecular hydrogen bonds. So between two xanthan gum molecules also there will be hydrogen bonding, and within the single xanthan gum also there will be hydrogen bonding, and because of that within the single molecule it starts forming a helical conformation. Okay. Okay. Now let's go on to question number 7. Consider two plates. One is made up of aluminium and other is made up of stainless steel. They are bonded together by an adhesive. Now, this bonded plates are pulled apart. Okay, and the material undergoes failure. Okay, and after these are pulled apart, and when the plates were observed, the separated plates had some exposed metal or alloy in case of stainless steel. So now identify what type of failure the material had. You are able to follow the question?
Yes, ma'am.
So two plates, one is a metal and other one is an alloy. These are bonded by an adhesive, a polymeric adhesive. Now this was pulled apart, and due to this pulling apart, the material failed and it got separated. And when it got separated, and when we observed that bonded area, you could see that there was some portion of the metal also exposed, or alloy also exposed. So what type of failure is this? This was discussed.
Joint failure.
Yes, there's a joint failure. Yes, that is why this is purposeful test of pulling apart and seeing the behavior of adhesive. Okay, now tell me what type of failure. So in adhesives, do you remember two types of failure was discussed? So what are those, and what is applicable in this case? You are able to recollect the lecture?
No, ma'am.
Okay, next I'll give you one more clue. There are two types of.
Adhesive failure
Who answered it?
from Nirmal.
Nirmal. So how do you say it is adhesive failure?
So the what can I say? The interaction between the adhesive and the metal plates is not good, not proper.
How do you say so? What made you say so? I'll say one more thing. You're right. Your answer is right.
Because the metal plates are exposed at the same time the the interaction between the adhesive and the metal plates also not good.
Yes, yes, you're right. So, so adhesive failure is the case in this one. So there are two types of failure of adhesive material. One is the cohesive failure, and the second one is the adhesive failure. So what happens in case of adhesive failure? How do you say it is adhesive failure in this case? Is that when the when you observe, when the separated plates was observed, so there was some exposed metal or alloy also, right? That means in that place the adhesive did not stick to the metal or alloy also, right? So obviously there is no proper adhesion of the adhesive with that material, and that is why we say adhesive failure. Whereas when do we say cohesive failure? Is that in similar case, when you just join two dissimilar materials, and when you pull apart and see, and in both sides if it is only the adhesive that is exposed, then there is a failure due to the cohesive failure. So within the adhesive there is a failure, that means it has stuck to the metal very well, but within the adhesive, due to the pulling force, the material has failed. Okay, so Udaya, you are able to get the point?
Yes, ma'am.
Yeah, see, cohesive forces within the material, within the material, like same material. Okay, whereas adhesive force is between two different materials. Okay, this you would have
Okay.
studied in your basic physics itself, like what are cohesive forces, what are adhesive forces, right? Yeah, now let's go on to next question. In addition to solvent diffusion, segmental relaxation, disentanglement, The dissolution of semi-crystalline polymer also involves, what is the additional thing? Semi-crystalline polymers, there will be much more complexity than amorphous polymer, right? What is that? That is what is the answer. Are you able to recollect? So solvent, diffusing of solvent, segmental
Chain
relaxation.
unfolding.
Yes, perfect. So in case of semi-crystalline polymer, there will be a lamella arrangement and chain arrangement. So that chain arrangement should also be removed by the solvent, right? For dissolution. So that is the additional task in case of a semi-crystalline polymer, or that is the additional complexity in case of dissolution of semi-crystalline polymer. Okay. Okay. Now let's go on to next question. Rate of polymerization in anionic polymerization is given by rate of Rp is equal to Kp into Ki by Kt power half, Ci power half, Cm, or is it rate of polymerization is equal to Kp into COH square, or is it rate of polymerization is equal to Kp into Cm, or is it D, option D, rate of polymerization is equal to Kp into COH square into Cm? Which of these is the right option for in case of anionic polymerization? This is again taken from your lecture.
Option A, ma'am.
Is it option A?
Yes, ma'am.
Both of you agree?
No, ma'am, option C.
Okay. Both of you should justify.
Because
Yeah. Tell me.
so option one is for free radical polymerization.
Okay.
Option C for living polymerization.
Is it
That is Rp, that is equal to Kp into Cm.
okay? So it is not in general for living polymerization, but it is more of a generic formula for anionic polymerization, because cationic polymerization, as I discussed in the recap, uh, it follows different rate. Okay, so
Okay.
option C is the right answer. Okay, yeah. Now tell me, Weissenberg number is given by, what is the definition for Weissenberg number? Do you remember there was a discussion on different dimensionless numbers like Reynolds number, and then your elastic number, Deborah number, and Weissenberg number? So what is this Weissenberg number?
Ma'am, strain rate into material time scale.
Yes, you are right. So your Weissenberg number is your strain rate into material times. Okay. So that's it for this week. Okay. So anything else you want to discuss? Udaya, I'll answer the question posted for in the forum, either through forum or in the next class. Okay. Uh, so anything else, or let's end the session.
Thank you.
Excellent.
Okay. Okay.
Hello, ma'am.
Yeah.
Ma'am, actually, I am from mechanical background.
Okay.
I'm doing my PhD in polymer composites.
Okay.
Uh, can you suggest some textbooks to read the basics,
Uh,
to study the basics for this course also?
okay. 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 For this polymers, I think there might be some books suggested in the this one. What is it?
Syllabus, course syllabus
Course
itself.
syllabus. You can just
Yes,
go
yes,
through
sir.
those books because those will be the best books. Okay.
Okay, okay, ma'am.
Yeah.
Sure. Okay, ma'am. Thank you.
Yeah. Thank you. Thank you all. Have a nice time.
Thank you.
Thank you. Thank you.